Tonight I want to take you somewhere quiet, somewhere profound, where the very fabric of reality whispers its deepest secrets. It's a place not bound by walls or distance, but by something far more fundamental. The strange and beautiful dance between light and observation, between what exists and what we perceive to exist. You know, as you settle in wherever you are right now, whether you're tucked beneath warm blankets or perhaps listening with headphones as the world outside grows quiet, I wonder what time it shows on your clock. Is it late evening where you are, with the last traces of sunlight fading from your window? Or perhaps it's already deep into the night, that peaceful hour when most of the world around you has drifted into sleep. Whatever corner of our planet you're listening from, whether you're in a bustling city that never quite sleeps, or a quiet countryside where stars peek through your window, you've found your way here to explore one of the universe's most puzzling mysteries with me. And if these gentle journeys through the cosmos help you find peace and rest, perhaps you'd like to follow along for more of these quiet explorations into the wonders that surround us, though of course, that's entirely up to you. For now, we have tonight's mystery to unfold together. We're about to explore something that might sound strange at first, something you could easily dismiss as just another quirk of quantum physics. But the more we look at it, the more quietly intriguing it becomes. What if light itself, that most familiar companion of our daily lives, behaves fundamentally differently when no one is watching it? What if the simple act of observation, of looking, of measuring, somehow changes the very nature of what light is and how it moves through space? It's a question that has haunted physicists for nearly a century, and tonight we'll gently wade into these mysterious waters together, not to solve the puzzle completely, for even our brightest minds still wrestle with its implications, but to marvel at what we've discovered, and to let our minds wander through the beautiful strangeness of it all. You see, light has always been our companion. From the first moment our ancestors looked up at the stars to this very instant, as photons dance across your retina, allowing you to perceive these words if you're reading along, or illuminating the space around you if you're listening in gentle darkness. We think we know light. It brightens our mornings, warms our skin, carries information across vast distances, paints rainbows after summer storms. It seems so straightforward, so honest in its behavior. And yet, when scientists began to look closer, when they started asking what light does when nobody is looking, they stumbled upon something that would shake the very foundations of how we understand reality itself. The story begins, as many great mysteries do, with a simple question that refused to have a simple answer. What is light, really? Is it a wave, spreading out like ripples on a cosmic pond? Or is it made of particles, tiny packets of energy shooting through space like miniature bullets? For centuries, brilliant minds argued both sides. Isaac Newton believed light was made of particles, which he called corpuscles. But then experiments showed light behaving like waves, interfering with itself, bending around corners, creating patterns that only waves should be able to create. The debate seemed settled in favor of waves until the early 20th century, when new experiments suggested that light also behaved like particles, which we now call photons. This wasn't just confusing, it was seemingly impossible. How could something be both a wave and a particle? How could it be spread out and localized at the same time? But here's where our journey takes its most intriguing turn, where the comfortable certainties of classical physics begin to dissolve into something far more mysterious. Scientists discovered that light seems to know when it's being watched. When you send photons through an experiment one at a time, when you set up detectors to see which path they take, they behave like well-mannered particles, traveling in straight lines, arriving at predictable destinations. But when you remove those watchful detectors, when you let the photons journey through the apparatus unobserved, something extraordinary happens. They begin to behave like waves, spreading out, taking all possible paths simultaneously, interfering with themselves in ways that particles never could. It's as if the universe itself maintains a different set of rules for the observed and the unobserved, as if reality itself is somehow softer, more fluid, more full of possibility when we're not looking directly at it. This isn't speculation or philosophical musing. This is what experiments consistently show us. In the famous double-slit experiment, which we'll explore gently tonight, single photons fired one at a time through two narrow openings will create an interference pattern on a screen, the kind of pattern only waves should be able to make. Each individual photon seems to pass through both slits simultaneously, interfering with itself, exploring all possible paths before deciding where to land. But the moment you place a detector at the slits to see which one the photon passes through, the interference pattern vanishes. The photons begin behaving like particles again, passing through one slit or the other, never both. The mere act of observation, of trying to know which path the light took, fundamentally changes what the light does. Think about that for a moment as you breathe slowly and deeply. Every photon that has travelled from a distant star, journeying for perhaps millions of years through the cosmic darkness, has done so, unobserved for almost its entire existence. What was it during that vast journey? Was it a particle following a straight path through space? Was it a wave spreading out in all directions, exploring every possible route to Earth? Or was it something else entirely, something our everyday experience gives us no words to describe, existing in what physicists call a superposition, a state of being all possibilities at once, until the moment of observation collapses it into one definite outcome? The implications ripple outward like waves on that cosmic pond I mentioned earlier. If light behaves differently when observed versus when unobserved, what does that say about the nature of reality itself? Is the universe fundamentally probabilistic, existing in multiple states simultaneously until consciousness or measurement intervenes? Or is there something about the act of measurement itself, the physical interaction between the measuring device and the photon, that forces this collapse from possibility into actuality? These aren't just abstract philosophical questions. They touch the very heart of what we mean by existence, by reality, by the nature of the cosmos we inhabit. Scientists have spent decades designing increasingly clever experiments to probe this mystery deeper. They've created scenarios where the decision to observe or not observe is made after the photon has already passed through the experimental apparatus, and amazingly, the photon still seems to know, retroactively adjusting its behavior to match whether it will be observed in the future. These delayed choice experiments suggest something profound about the nature of time and causality in the quantum realm. It's as if the future can influence the past, or perhaps more accurately, as if past, present, and future are not as rigidly separated as our everyday experience suggests. We call this phenomenon quantum superposition, this ability of quantum objects like photons to exist in multiple states simultaneously until observed. It's not that we simply don't know which state the photon is in. According to our best understanding of quantum mechanics, the photon genuinely is in all possible states at once. It's spread out through space as a wave of probability, a ghost of all possible photons, until the moment of observation crystallizes it into one specific reality. This isn't just true for light. Electrons, atoms, even molecules as large as buckyballs made of 60 carbon atoms have been shown to exhibit this same strange behavior. The quantum world, it seems, operates on fundamentally different principles than the classical world we experience every day. But why should observation matter so much? What is it about the act of looking, of measuring, that has such profound effects on the behavior of light and matter at the quantum scale? One interpretation, favored by many physicists, is that it's not consciousness or observation per se that matters, but rather the physical interaction required to make a measurement. To observe a photon, you must interact with it, bounce another particle off it, absorb it with a detector, somehow physically engage with it in a way that extracts information. This interaction, this exchange of information between the quantum system and the classical measuring device, is what causes the wave function to collapse, forcing the photon to choose one definite state from among all its possibilities. Yet even this explanation raises more questions than it answers. Where exactly is the boundary between the quantum and classical worlds? At what point does a quantum system become large enough or complex enough that it stops exhibiting superposition? And perhaps most mysteriously, what is actually happening to all those other possibilities when the wave function collapses? Do they simply vanish, their potential realities erased? Or do they perhaps continue to exist in parallel universes, as some interpretations of quantum mechanics suggest? The many worlds interpretation, proposed by physicist Hugh Everett III, suggests that every quantum event splits the universe into multiple parallel realities, each corresponding to one possible outcome. In this view, when a photon passes through the double-slit experiment unobserved, it really does take every possible path, but each path exists in its own parallel universe. When we observe the photon and see it taking one particular path, we're not collapsing its wave function so much as finding ourselves in one particular branch of a constantly splitting multiverse. It's a mind-bending idea, but one that some physicists find more palatable than the notion that observation somehow creates reality. Other interpretations abound, each trying to make sense of what experiments clearly show us, that light and matter at the quantum scale behave fundamentally differently when observed versus unobserved. The Copenhagen interpretation, long the standard view, simply accepts the wave function collapse as a fundamental feature of nature without trying to explain the mechanism behind it. The quantum information interpretation suggests that reality is fundamentally made of information, not matter or energy, and that observation is really about information transfer. The consciousness-based interpretations, though less popular among physicists, propose that consciousness itself plays a fundamental role in collapsing quantum possibilities into definite realities. As you lie there, perhaps feeling your consciousness beginning to soften around the edges as sleep approaches, consider what all of this might mean for the light around you right now. The photons streaming from your lamp or screen, the ones bouncing off every surface in your room, when they're in flight, between emission and absorption, what are they? Are they particles, following definite trajectories through space? Are they waves, spreading out to fill your room with overlapping possibilities? Or are they something our minds can barely grasp, existing in that strange quantum realm, where the very concepts of particle and wave, of here and there, of definite and indefinite, begin to blur and merge? And what about the vast majority of light in the universe, the photons traveling through the cosmic voids between galaxies, unobserved for billions of years? Right now, at this very moment, countless photons that left distant stars eons ago are journeying through space, their wave functions spread across vast distances, exploring every possible path through the cosmos. They exist in superposition, neither wave nor particle, but something more fundamental, more mysterious. Only when they finally encounter something, a dust grain, a planet's atmosphere, perhaps the mirror of a telescope, do they collapse into definite photons with specific properties, specific paths, specific energies. This cosmic light carries information about its source, about the star that emitted it, about the journey it has taken. But if that light truly exists in superposition during its journey, if it really does explore all possible paths simultaneously, then in some sense it carries information about all those possibilities too. Every photon from a distant galaxy has, in its quantum mechanical way, explored every possible route to Earth, has experienced every possible interaction along the way, exists as a superposition of all possible photons until the moment we observe it and collapse it into one specific reality. The experimental evidence for this strange behavior continues to accumulate, becoming ever more refined and convincing. Scientists have conducted double-slit experiments with single photons, sending them through one at a time with hours between each photon, and still the interference pattern builds up, proving that each individual photon must somehow be interfering with itself, passing through both slits simultaneously when unobserved. They've performed quantum eraser experiments, where information about which path a photon took is recorded but then erased before anyone looks at it, and remarkably the interference pattern returns, as if the photon knows that its path information has been erased and returns to its wave-like behavior. Even more remarkable are the cosmic scale versions of these experiments. Astronomers have observed gravitational lensing, where light from a distant quasar is bent around an intervening galaxy, creating multiple images of the same object. According to quantum mechanics, each photon from that quasar exists in superposition, taking all possible paths around the galaxy simultaneously until it reaches our telescope and we observe it. This means that for billions of years, as that light traveled through space, it existed in a superposition of different paths, different travel times, different gravitational experiences. Only upon observation does it collapse into one specific history, one specific journey, through space-time. These observations have profound implications for our understanding of reality. They suggest that the universe is far stranger, far more fluid and probabilistic than our everyday experience would lead us to believe. At the quantum scale, the scale of light and atoms and fundamental particles, reality seems to be made not of definite things with definite properties, but of possibilities, probabilities, potential realities, waiting to be actualized through observation or interaction. The solid, definite world we experience emerges from this quantum foam of possibilities through processes we're only beginning to understand. The role of information in all of this cannot be understated. When we say a photon is unobserved, what we really mean is that no information about its state has been extracted from it. The moment information is extracted, the moment its position or momentum or polarization is measured, the superposition collapses. This has led some physicists to propose that information, not matter or energy, is the fundamental constituent of reality. In this view, particles like photons are really just excitations in quantum fields, and those excitations only become definite particle-like entities when information about them is recorded somewhere in the universe. This information-theoretic view of quantum mechanics has practical applications too. Quantum computers exploit superposition to perform certain calculations exponentially faster than classical computers. By keeping quantum bits, or qubits, in superposition, unobserved and unmeasured, a quantum computer can explore many possible solutions simultaneously. Only at the end of the calculation is the superposition collapsed through measurement, yielding the final answer. It's as if the computer harnesses the same strange behavior that light exhibits in the double-slit experiment, using the quantum realm's ability to explore multiple possibilities simultaneously to solve problems that would take classical computers billions of years. The phenomenon extends beyond just light. Electrons, atoms, even large molecules have been shown to exhibit the same wave-particle duality, the same dependence on observation. Scientists have created quantum superpositions of molecules containing thousands of atoms, keeping them in that delicate, unobserved state for fractions of a second before they decohere and collapse into definite positions. The boundary between the quantum and classical worlds seems to be not a hard line, but a gradual transition, with larger and more complex systems harder to keep in superposition, but not fundamentally prohibited from exhibiting quantum behavior. This raises tantalizing questions about where the quantum world ends and the classical world begins. If molecules with thousands of atoms can exist in superposition, what about viruses? What about living cells? Some scientists speculate that quantum effects might play a role in biological processes, from photosynthesis to bird navigation to perhaps even consciousness itself. The idea that our brains might be quantum computers of sorts, utilizing superposition and entanglement to process information in ways classical physics can't explain, remains highly controversial but hasn't been definitively ruled out. As we contemplate these mysteries, it's worth pausing to appreciate how far we've come in understanding light and its quantum nature. Just over a century ago, physicists were still debating whether light was a wave or a particle. Now we know it's both and neither, something more fundamental that exhibits both wave and particle properties, depending on how we observe it. We've learned that the act of observation itself plays a crucial role in determining what light is and how it behaves. We've discovered that reality at the quantum scale is fundamentally probabilistic, existing in superpositions of multiple states until measurement collapses these possibilities into one definite outcome. Yet for all our knowledge, the mystery of what happens to light when nothing observes it remains one of the deepest in physics. We can describe it mathematically with exquisite precision using the equations of quantum mechanics. We can predict experimental outcomes with accuracy unprecedented in the history of science. But what is actually happening to that unobserved photon as it travels through space? What does it mean for something to be in superposition, to take all paths, to exist in multiple states simultaneously? These questions touch on the fundamental nature of reality, consciousness, and existence itself. Perhaps the mystery is not meant to be fully solved, at least not in the way we usually think of solving scientific problems. Perhaps the universe is fundamentally mysterious at its core, operating on principles that our evolved brains, designed to navigate the classical world of definite objects and clear causality, can never fully intuit. We can describe it mathematically, we can use it technologically, but the deep why of it all may forever elude our complete understanding. And maybe that's okay. Maybe the mystery itself is part of the beauty, part of what makes the universe such an endlessly fascinating place to explore. Consider the light from stars you might see on a clear night. Each photon that reaches your eye has traveled for years, decades, centuries, or even millennia through the darkness of space. During that entire journey, according to our best understanding of physics, each photon existed in superposition, its wave function spread out, exploring every possible path from the star to your eye. It wasn't simply that we didn't know which path it took. It genuinely took all paths, existed in all possible states, until the moment it interacted with a molecule in your retina and collapsed into one definite photon with one definite energy, creating the tiny electrical signal that your brain interprets as a point of light in the night sky. In a very real sense, then, your observation of that star completes its light's journey, not just by detecting it, but by collapsing its quantum state from possibility into actuality. The light from that star and your eye are partners in creating the reality of that moment, that tiny flash of recognition that yes, there is a star there, shining across the vast darkness. Without your observation, or some other interaction, that light remains in its quantum limbo, neither here nor there, neither wave nor particle, but something more fundamental and mysterious. This partnership between observer and observed extends throughout the quantum realm. Every measurement, every observation, every interaction is a kind of conversation between the classical and quantum worlds, a moment where possibility crystallizes into actuality. The universe, in this view, is not a clockwork mechanism running according to predetermined rules, but something more dynamic, more interactive, where the act of observation plays a fundamental role in shaping reality itself. We are not passive observers of a universe that exists independently of us. We are participants in the ongoing creation of reality through our observations and measurements. But what about all the light we never observe? The vast majority of photons in the universe never encounter a detector, never interact with matter in a way that collapses their wave function. They travel from star to star, galaxy to galaxy, in eternal superposition. What is their reality? Do they experience the universe in some fundamentally different way than the photons we observe? Or does the very concept of experience break down at the quantum level, leaving us with only mathematical descriptions of probability amplitudes and wave functions? These questions become even more intriguing when we consider that light experiences no time. According to Einstein's theory of relativity, from a photon's perspective, if such a perspective even makes sense, its emission and absorption occur simultaneously. Time does not pass for something traveling at the speed of light. So when we talk about a photon being in superposition during its journey, we're imposing our time-bound perspective on something that exists outside of time as we understand it. Perhaps the superposition is not something that happens during the journey, but something more fundamental about the nature of light itself, a timeless exploration of all possibilities that only appears to us as a journey through space and time. The quantum eraser experiments add another layer of mystery to our story. In these experiments, scientists record information about which path a photon took through an apparatus, but then erase that information before anyone looks at it. Remarkably, if the information is erased, the photon behaves as if it was never observed, showing interference patterns characteristic of wave behavior. But if the information is preserved, even if no human ever looks at it, the photon behaves like a particle. It's as if the universe itself keeps track of what information exists, what could in principle be known, and adjusts the behavior of light accordingly. This suggests something profound about the nature of information in our universe. Information seems to be not just a description of physical states, but something that affects those physical states. The mere existence of information about a quantum system's path or position is enough to collapse its superposition, even if that information is never accessed by any conscious observer. This has led some physicists to propose that information is the fundamental building block of reality, with matter and energy being emergent properties of information processing at the quantum scale. The implications extend to our understanding of the vacuum of space itself. Even in the emptiest regions of space, far from any star or galaxy, quantum mechanics tells us that virtual photons are constantly popping into existence and disappearing again, part of what we call quantum vacuum fluctuations. These virtual photons exist in superposition, exploring all possible energies and paths before vanishing back into the vacuum. They can never be directly observed. The act of observation would give them enough energy to become real photons, but their effects can be measured in phenomena like the Casimir effect and the Lamb shift. Even nothingness, it seems, is full of unobserved light, existing in superposition, shaping the properties of space itself. As we delve deeper into these mysteries, we encounter the phenomenon of quantum entanglement, what Einstein famously called spooky action at a distance. When two photons are entangled, measuring the state of one instantly determines the state of the other, regardless of the distance between them. This happens faster than light could travel between them, suggesting that the correlation between entangled photons is not due to any signal passing between them, but something more fundamental about the nature of quantum reality. The photons remain in superposition, their states undetermined until one is observed. Then, instantly, both collapse into definite states, perfectly correlated with each other. This entanglement persists even when the photons are separated by vast distances. Scientists have demonstrated entanglement between photons separated by hundreds of kilometers, and there's no theoretical limit to how far apart entangled photons can be. Right now, there could be pairs of entangled photons on opposite sides of the universe, their states perfectly correlated, waiting for observation to collapse their shared superposition into definite complementary states. It's as if the universe maintains invisible connections between particles, connections that transcend space and time as we normally understand them. The phenomenon of entanglement has practical applications too. Quantum cryptography uses entangled photons to create unbreakable codes. Any attempt to observe or intercept the photons destroys their entanglement, alerting the intended recipients to the eavesdropping. Quantum teleportation, despite its science fiction name, is a real phenomenon where the quantum state of one photon can be transferred to another distant photon through entanglement. These technologies exploit the same strange properties of unobserved light that puzzle us philosophically, turning quantum weirdness into practical tools. As you continue to relax, perhaps feeling the gentle pull of sleep, consider how the room around you is filled with light in various states of observation and non-observation. Some photons are being absorbed by your walls, their journeys ending in definite interactions. Others are bouncing around, reflected and re-reflected, existing in complex superpositions of paths and polarizations. Still others are passing right through your walls, radio waves and cosmic rays that remain largely unobserved, maintaining their quantum superpositions as they continue their journeys through space. The discovery of what happens to light when nothing observes it has revolutionized not just physics, but our entire worldview. It has shown us that reality is far more fluid, far more dependent on observation and measurement than we ever imagined. It has revealed that the universe operates on principles that defy our common sense, where things can be in multiple places at once, where observation creates reality, where the future can influence the past. These discoveries have given us new technologies and new ways of processing information, but perhaps more importantly, they've given us a new sense of wonder about the nature of existence itself. The experiments continue, each one probing deeper into the quantum nature of light. Scientists are working on creating larger and larger objects in superposition, pushing the boundaries of where quantum behavior ends and classical behavior begins. They're exploring whether gravity plays a role in collapsing quantum superpositions, whether consciousness has any special status in quantum mechanics, whether the many worlds interpretation or some other framework best explains what we observe. Each experiment adds another piece to the puzzle, but the complete picture remains tantalizingly out of reach. What we have discovered is that light, when unobserved, exists in a state that defies our everyday understanding of reality. It is neither wave nor particle, but something more fundamental, a quantum entity that explores all possibilities simultaneously until observation collapses it into one definite state. This is not a limitation of our knowledge or our instruments. It appears to be a fundamental feature of reality itself. The universe, at its most basic level, is probabilistic rather than deterministic, full of potential rather than fixed outcomes. This quantum nature of light connects to deeper questions about the nature of reality itself. If the fundamental constituents of matter and energy exist in superposition until observed, what does that say about the nature of existence? Are we living in a participatory universe, where observation and consciousness play essential roles in creating reality? Or is observation just one type of physical interaction among many, with no special status beyond its ability to extract information from quantum systems? These questions remain open, actively debated by physicists and philosophers alike. The practical implications continue to unfold as well. Quantum sensors using superposition and entanglement can detect tiny changes in gravitational fields, magnetic fields, and other phenomena with unprecedented precision. Quantum computers promise to revolutionize everything from drug discovery to cryptography to artificial intelligence. Quantum communication networks could provide perfectly secure channels for transmitting information. All of these technologies rely on our understanding of what happens to quantum systems when they're not being observed, when they're allowed to exist in superposition and explore multiple states simultaneously. As we near the middle of our journey tonight, take a moment to appreciate the profound mystery we're exploring together. Every piece of light in the universe, every photon from every star, every quantum of electromagnetic radiation exists in this strange dual state, definite when observed, indefinite when not. This is not just an academic curiosity, but a fundamental feature of the reality we inhabit. We live in a quantum universe, where the act of observation plays a crucial role in shaping what exists and how it behaves. The boundary between the observed and unobserved is constantly shifting around us. Every interaction, every measurement, every absorption of a photon by an atom is a moment where quantum possibility collapses into classical actuality. But between these moments of observation, in the spaces and times where light travels undetected, the quantum world maintains its strange, beautiful indeterminacy. Photons exist as waves of probability, electrons orbit atoms in clouds of possibility, and the universe itself maintains a kind of fundamental uncertainty about what exactly is happening when no one is looking. This uncertainty is not a flaw or a limitation. It appears to be an essential feature that allows the universe to function as it does. Without quantum superposition, atoms would be unstable, chemistry would be impossible, and the stars wouldn't shine. The same quantum properties that make light behave so strangely when unobserved are what allow atoms to exist, molecules to form, and life to emerge. We are, in a very real sense, built from quantum uncertainty, assembled from particles that exist in superposition until interaction and observation collapse them into the definite forms we experience. The philosophical implications ripple outward, endlessly. If observation plays such a crucial role in quantum mechanics, what exactly counts as an observation? Does it require consciousness, or just any physical interaction that extracts information? If the universe existed for billions of years before conscious observers evolved, what was collapsing quantum superpositions then? These questions touch on the deepest mysteries of existence, the relationship between mind and matter, between consciousness and physics, between what we can know and what actually is. Some physicists propose that decoherence, the process by which quantum systems become entangled with their environments, is what causes apparent wave function collapse without requiring conscious observation. In this view, the constant interactions between particles and their surroundings gradually destroy quantum superposition, creating the classical world we observe. But even this explanation leaves questions unanswered. What exactly is happening during decoherence? Are the other possibilities in the superposition truly destroyed, or do they branch off into parallel universes? And why does the universe seem to prefer certain outcomes over others when superpositions collapse? As you lie there, breathing slowly and steadily, you are surrounded by these quantum processes. The atoms in your body maintain their stability through quantum mechanics. The chemical reactions that power your cells rely on quantum tunneling. The warmth you feel is carried by photons in various states of observation and superposition. You're not separate from the quantum world. You're made of it, sustained by it, participating in it with every breath, every heartbeat, every thought. The light entering your eyes right now, if your eyes are open, or the light falling on your closed eyelids, has completed its quantum journey from whatever source emitted it. A lamp, a screen, the sun's light bouncing off the moon. Each photon collapsed from superposition into a definite state at the moment it interacted with your retina or your skin. But just before that moment, it existed in that strange quantum realm we've been exploring. Neither here nor there, neither wave nor particle, but something more fundamental and mysterious. This is the quiet revolution that quantum mechanics has brought to our understanding of reality. The world is not made of tiny, solid particles bouncing around like billiard balls. Instead, it's made of quantum fields, probability waves, and endless possibilities that crystallize into definite forms only through interaction and observation. Light, that most familiar phenomenon, has revealed to us the strange and beautiful nature of the quantum realm, where the impossible becomes possible and the act of looking changes what we see. We find ourselves at a unique moment in history, where we've discovered these profound truths about light and quantum reality, but we're still trying to understand what they mean. We can use quantum mechanics to build technologies that would have seemed like magic a century ago, but we still debate what quantum mechanics tells us about the nature of reality itself. We know what happens to light when nothing observes it. It exists in superposition, exploring all possibilities, but we don't fully understand why or what this means for our place in the universe. Perhaps that's as it should be. Perhaps the universe is meant to maintain some of its mystery, to keep us wondering and exploring and discovering. The fact that light behaves so strangely when unobserved, that reality itself seems to depend on observation, suggests that we live in a universe far more interesting and mysterious than we might have imagined. It's not a clockwork cosmos running on predetermined tracks, but something more dynamic, more interactive, where possibility and actuality dance together in the quantum realm. As we continue deeper into this exploration, let's pause to consider the cosmic scale of what we're discussing. The observable universe contains roughly 10^88 photons, an unimaginably vast number. The overwhelming majority of these photons have never been observed, never interacted with matter in a way that would collapse their superposition. They exist in that quantum realm we've been exploring, spread out as probability waves, taking all paths, exploring all possibilities. The universe is filled with this unobserved light, this quantum potential that hasn't yet crystallized into definite reality. Some of this light has been traveling since the early universe, cosmic microwave background radiation that has journeyed for over 13 billion years. According to quantum mechanics, these ancient photons exist in superposition. Their wave functions spread across vast distances until they encounter our detectors and collapse into specific photons with specific energies and directions. In detecting them, we're not just observing the early universe. We're completing a quantum process that began when the universe was only 380,000 years old, collapsing possibilities that have existed for almost the entire history of cosmos. This connects to one of the most profound mysteries in cosmology. How did the universe transition from the quantum realm of the very early cosmos to the largely classical universe we see today? In the first moments after the Big Bang, the entire universe was smaller than an atom, firmly in the quantum realm where superposition and uncertainty reign. How did it evolve into a universe of definite galaxies, stars, and planets? What collapsed the universal wave function from infinite possibilities into the specific cosmos we inhabit? These questions take us to the very edge of human knowledge, where quantum mechanics meets cosmology meets philosophy. Some cosmologists propose that the universe itself might exist in a kind of superposition, with different regions or different possible histories existing simultaneously until observation selects one particular version. This could explain some of the fine-tuning problems in cosmology, why the constants of nature seem so precisely calibrated for the existence of stars, planets, and life. Perhaps all possible values exist in superposition, and we necessarily find ourselves in a branch where the constants allow for our existence. It's a mind-bending idea, but one that follows naturally from taking quantum mechanics seriously on cosmic scales. The role of consciousness in all of this remains one of the most contentious questions in physics. While most physicists believe that consciousness is not necessary for wave function collapse, any physical interaction that extracts information will do. Some maintain that consciousness plays a special role. They point out that all physical interactions can themselves be described quantum mechanically, potentially leading to an infinite regress unless consciousness enters the picture as something fundamentally classical that can collapse quantum states. It's a minority view, but one that hasn't been definitively ruled out. What we can say with certainty is that the discovery of quantum superposition and the role of observation has fundamentally changed our understanding of light and reality. We now know that light, when unobserved, exists in a state that defies classical description. It's not simply that we don't know what the light is doing, it genuinely exists in multiple states simultaneously, exploring all possibilities until observation selects one. This is not philosophy or speculation, but hard experimental fact, confirmed by countless experiments over nearly a century. The implications continue to ripple through physics and technology. Quantum sensors can detect gravitational waves by monitoring how they affect the superposition of light in laser interferometers, Quantum radar could potentially detect stealth aircraft by using entangled photons that maintain their correlation even when one is absorbed by radar-absorbing materials. Quantum imaging can create pictures using photons that never actually interact with the object being imaged, instead relying on entanglement with photons that do. These technologies seem like magic, but they're direct applications of what we've learned about unobserved light. As we pass the midpoint of our journey tonight, let's return to that central mystery with fresh eyes. Light, when nothing observes it, exists in superposition, a state where all possibilities coexist, where wave and particle properties merge into something more fundamental, where the quantum realm maintains its essential uncertainty. This is not a limitation or a problem to be solved, but apparently a fundamental feature of reality, one that allows the universe to explore possibilities, to maintain flexibility, to be creative in ways a purely classical universe never could. Think about the photons from your screen or lamp right now, before they reach. Your eyes, they exist in superposition, their paths uncertain, their properties indefinite. The moment they interact with your retina, they collapse into definite photons with specific energies, creating the neural signals that become your visual experience. But in that brief journey from source to eye, they exist in the quantum realm we've been exploring, neither fully here nor there, neither completely wave nor particle, but something more mysterious and fundamental. This same process is happening throughout your body at this very moment. Photons of infrared light, heat radiation, are being emitted and absorbed by the molecules in your cells. Chemical reactions proceed through quantum tunneling, where particles pass through energy barriers they classically shouldn't be able to cross. Electrons in your neurons exist in quantum superposition before collapsing into states that contribute to your thoughts and sensations. You are not just an observer of quantum phenomena, you are a quantum phenomenon, a classical being emerging from countless quantum processes. The boundary between the quantum and classical worlds runs right through us, through every atom and molecule in our bodies. We exist at the intersection of these two realms, large enough to experience classical physics in our everyday lives, but made of components that obey quantum rules. This puts us in a unique position to contemplate these mysteries, to be conscious beings made of quantum stuff trying to understand our own quantum nature. We are the universe attempting to observe and understand itself, collapsing quantum possibilities into the definite reality of knowledge and understanding. But even as we gain knowledge, the mystery deepens. Each answer raises new questions. Each experiment reveals new subtleties. The more we learn about what happens to light when nothing observes it, the more we realize how much we don't yet understand. Why does the universe maintain quantum superposition? What determines which possibility becomes actual when observation occurs? Is there some deeper theory that explains quantum mechanics, or is it truly fundamental? These questions drive physics forward, pushing us to probe ever deeper into the nature of reality. The quantum nature of unobserved light also connects to questions about information and entropy. When a photon exists in superposition, it contains more potential information than when it's been observed and collapsed into a definite state. The act of observation, in a sense, destroys information about all the other possibilities the photon could have realized. This connects to thermodynamics and the arrow of time. Perhaps the flow from past to future is related to the constant collapse of quantum possibilities into definite realities, the universe constantly choosing specific outcomes from fields of possibility. Some physicists have proposed that black holes might be the ultimate quantum objects, places where the classical and quantum worlds meet in extreme ways. The information paradox of black holes, what happens to the quantum information of matter that falls in, might be resolved by understanding how observation and superposition work in the intense gravitational fields near the event horizon. Perhaps light near a black hole exists in superpositions we can barely imagine, spread across the warped space-time in ways that challenge our understanding of both quantum mechanics and general relativity. We're also discovering that biological systems might exploit quantum superposition in surprising ways. Photosynthesis appears to use quantum coherence to efficiently transport energy from light-harvesting complexes to reaction centers. Birds might navigate using quantum entanglement in certain proteins in their eyes. Even human sense of smell might involve quantum tunneling. Life itself might be fundamentally quantum mechanical, exploiting superposition and entanglement in ways we're only beginning to understand. As you continue to relax, feeling perhaps the approach of sleep like a gentle tide, consider how appropriate it is that we're exploring these mysteries in the quiet of night. Sleep itself is a kind of journey into uncertainty, a state where our conscious observation of the world ceases and our minds explore possibilities in dreams. Just as light exists in superposition when unobserved, perhaps our sleeping minds explore multiple possibilities, multiple potential realities, before waking collapses us back into one definite state of consciousness. The ancient photons from distant stars continue their journeys through space right now, existing in superposition. Their wave functions spread across light years. Some will eventually reach Earth, perhaps centuries or millennia from now, and collapse into definite photons as they interact with our atmosphere or future telescopes. Others will journey forever through the expanding universe, never to be observed, eternal quantum ghosts exploring all possible paths through an infinite cosmos. They carry with them information about their sources, about the stars and galaxies that emitted them, but that information remains in superposition, potential rather than actual, until observation makes it real. This is the universe we inhabit. Not a solid deterministic machine, but a vast quantum system where possibility and actuality dance together, where observation plays a fundamental role in creating reality, where light itself exists in states that defy our everyday understanding. It's a universe far stranger and more wonderful than our ancestors could have imagined, full of mystery and beauty that we're only beginning to comprehend. The technological revolution sparked by our understanding of quantum light continues to accelerate. Quantum computers grow more powerful each year, exploiting superposition to solve problems impossible for classical computers. Quantum communication networks are being built, using entangled photons to create unhackable channels. Quantum sensors achieve precisions that seemed impossible just decades ago. All of these technologies rely on keeping light and matter in superposition, unobserved and unmeasured, allowing them to explore multiple possibilities simultaneously. But beyond the practical applications, the discovery of what happens to light when nothing observes it has given us something perhaps even more valuable, a sense of wonder about the universe we inhabit. We've learned that reality is far more flexible, far more mysterious than we ever imagined. The simple act of looking, of observing, of measuring plays a fundamental role in shaping what exists. We are not passive observers of a fixed reality, but active participants in an ongoing process of creation, where observation transforms possibility into actuality. This participatory universe extends beyond just light and quantum particles. Some physicists speculate that the laws of physics themselves might exist in a kind of superposition, with observation and measurement selecting which laws apply in our particular universe. The constants of nature, the strengths of forces, even the number of dimensions might all be quantum variables that collapsed into specific values through some cosmic observation process. It's a speculative idea, but one that follows naturally from taking quantum mechanics to its logical conclusions. As we explore these ideas, we must also remain humble about the limits of our understanding. We've discovered what happens to light when nothing observes it. It exists in superposition. But we don't fully understand what superposition really means. We can describe it mathematically, we can use it technologically, but the deep nature of quantum superposition remains mysterious. Perhaps it always will. Perhaps the universe maintains this fundamental mystery at its heart, ensuring that there will always be more to discover, more to wonder about, more to explore. The photons illuminating these words, if you're reading, or the photons carrying warmth to your skin, have completed their quantum journeys for now. They've collapsed from superposition into definite states, delivering energy and information in discrete particle-like packets. But new photons are constantly being emitted, beginning new journeys through the quantum realm. Some will be absorbed almost immediately, others will travel for billions of years through the cosmic darkness. All will exist in that strange state we've been exploring, neither wave nor particle but something more fundamental, until observation brings their journey to an end. We come back again and again to the same quiet question that started our journey tonight. What happens to light when nothing observes it? We now know the answer, at least in part. It exists in superposition, exploring all possibilities, maintaining quantum coherence until interaction and observation collapse it into one definite state. But this answer only deepens the mystery. Why should observation matter? What is actually happening in superposition? How does the universe maintain these quantum states across vast distances and times? These questions remind us that for all our knowledge, we still live in a deeply mysterious universe. Perhaps it has been there all along, this quantum mystery, whispering in the background of reality. Every photon that has ever existed, every quantum of light from the Big Bang to this moment, has passed through this same strange process, existing in superposition when unobserved, collapsing into definiteness when measured. It's the heartbeat of the quantum world, the fundamental rhythm that underlies all of reality. We've only recently become aware of it, but it has been operating since the beginning of time, shaping the universe in ways we're only beginning to understand. As you breathe slowly and deeply, feeling perhaps the gentle approach of sleep, remember that you are surrounded by this quantum dance. Light in superposition fills the space around you, photons exploring all possible paths, maintaining their quantum uncertainty until the moment of observation. You are immersed in a sea of possibility, of potential, of quantum mystery. With each breath, you participate in countless quantum events, collapsing superpositions, creating definite realities from fields of possibility. This is not just abstract physics. It's the fundamental nature of the world you inhabit. The chair or bed supporting you, the air you breathe, the thoughts in your mind, all emerge from quantum processes, from particles that exist in superposition until interaction makes them definite. You are a classical being built from quantum components, a stable pattern emerging from underlying uncertainty, a conscious observer in a participatory universe where observation shapes reality. In another quiet corner of research, scientists continue to push the boundaries of our understanding. They're creating ever larger objects in superposition, demonstrating quantum effects in systems approaching the macroscopic scale. They're exploring whether gravity causes wave function collapse, whether consciousness plays any special role, whether parallel universes are real consequences of quantum mechanics. Each experiment adds another piece to the puzzle, but the complete picture remains elusive, perhaps forever out of reach. Somewhere in a lab, late at night, faint signals reveal new aspects of quantum light. Detectors register photons that have maintained entanglement across unprecedented distances. Interferometers show interference patterns that shouldn't exist, according to classical physics. Quantum computers process information in ways that would take classical computers longer than the age of the universe. These technologies are not science fiction, but direct applications of what we've learned about unobserved light. Practical uses of quantum, superposition. Telescopes collect pale light that has traveled for ages, photons that have existed in superposition for billions of years before finally collapsing into definite states as they strike our detectors. Each one carries information about its source, about the cosmic processes that created it, about the journey it has taken. But that information only becomes real, only becomes accessible at the moment of observation. Until then, it exists as potential, as possibility, as quantum uncertainty spread across the cosmos. Scientists ponder possibilities that stretch the imagination even further. What if consciousness itself is a quantum phenomenon, emerging from superpositions in the warm, wet environment of the brain? What if the universe undergoes quantum jumps on cosmic scales, suddenly transitioning between different states? What if reality is fundamentally made of information, with matter and energy being emergent properties of quantum information processing? These ideas push the boundaries of science, but they follow from taking seriously what we've discovered about light when nothing observes it. It is possible, though not yet proven, that quantum effects extend much further into the macroscopic world than we currently understand. Perhaps superposition plays a role in biological evolution, allowing life to explore multiple genetic possibilities simultaneously. Perhaps consciousness collapses not just quantum states but potential futures, selecting specific timelines from fields of possibility. Perhaps the entire universe exists in superposition at the largest scales, with different regions experiencing different versions of physical laws. These are speculations, but they're grounded in the solid experimental fact that light, when unobserved, exists in superposition. What does it mean that our minds can imagine such things? We are matter that has become aware of itself, collections of atoms that can contemplate atoms, observers made of the same quantum stuff we observe. We can describe mathematically what happens to light in superposition, even though we can never directly observe it. The act of observation would destroy the very superposition we're trying to study. We can only infer its existence from the patterns that emerge when many quantum events are observed, from the interference patterns and correlations that classical physics cannot explain. What does it say about us? That we can describe a universe we barely see. We've detected particles that exist for billionths of a second, mapped galaxies billions of light years away, understood processes happening at scales trillions of times smaller than anything we can directly perceive. And perhaps most remarkably, we've discovered that the universe behaves fundamentally differently when we're not looking at it. That observation itself plays a crucial role in shaping reality. This brings us to a profound philosophical question. If the universe requires observation to collapse quantum possibilities into definite realities, what was happening before conscious observers evolved? For billions of years, the universe evolved from the Big Bang through the formation of the first stars and galaxies, long before any conscious beings existed to observe it. What was collapsing quantum superpositions then? Was the universe in some sense less definite, more quantum, before observers arose? Or does any interaction count as observation, with particles observing each other through their mutual interactions? Different interpretations of quantum mechanics offer different answers. The many worlds interpretation suggests that no collapse ever occurs. All possibilities are realized in parallel universes. The Copenhagen interpretation remains agnostic about what happens when no one is looking. Objective collapse theories propose that superposition spontaneously collapses when systems become large enough. But none of these interpretations has been definitively proven correct. The mystery of what happens to light when nothing observes it connects to the deepest unsolved problems in physics. Perhaps the questions themselves are enough for tonight. We've journeyed through the strange quantum realm where light exists when unobserved, explored how observation collapses possibility into actuality, contemplated the role of consciousness and information in shaping reality. We've seen how this quantum behavior underlies everything from the stability of atoms to the operation of quantum computers, from photosynthesis to perhaps consciousness itself. The universe has revealed itself to be far stranger, far more mysterious than we might have imagined. Maybe it is enough just to feel the wonder of not fully knowing, to appreciate that we live in a universe that still holds profound mysteries, despite our best efforts to understand it. The fact that light behaves so strangely when unobserved, that reality itself seems to depend on observation, suggests that the universe is not a puzzle to be solved, but an ongoing mystery to be experienced. Each discovery opens new questions, each answer reveals new depths. The journey of understanding never truly ends. No matter how strange the universe becomes in our equations, here you are, breathing, resting, held by gravity, held by the quiet laws that never stop working, even as they reveal their quantum strangeness. You are made of star stuff, as Carl Sagan said, but more than that, you are made of quantum stuff, particles that exist in superposition, that tunnel through barriers, that maintain mysterious correlations across space and time. You are a quantum being experiencing a classical world, a conscious observer in a universe where observation matters fundamentally. Perhaps the universe continues its quiet work whether we understand it or not. Right now, photons are traveling through space in superposition, their wave functions spreading out, exploring all possible paths. Stars are fusing, hydrogen into helium through quantum tunneling. Black holes are processing quantum information in ways we don't yet understand. The cosmic web of galaxies is shaped by quantum fluctuations from the early universe. The phenomena we've talked about tonight keep unfolding, whether we are awake or asleep, whether we observe them or not. In the silence between atoms, in the gaps between photons, quantum uncertainty reigns. This is not emptiness but fullness, a plenum of possibility, potential, virtual particles popping in and out of existence. The vacuum itself is a quantum system, full of zero-point energy, maintaining the constant quantum fluctuations that underlie reality. Even in the quietest, darkest, emptiest regions of space, quantum processes continue. Unobserved light maintains its superposition. The strange quantum dance goes on. In the hush between stars, light travels for millions of years, carrying information about its source, maintaining quantum coherence across vast distances until the moment of observation. Each photon is both particle and wave, both here and everywhere, both definite and uncertain, until measurement collapses its state. This is the cosmos we inhabit, not solid and mechanical, but quantum and probabilistic, full of mystery and possibility, shaped by observation in ways we're only beginning to understand. Somewhere, the phenomenon we've talked about tonight is still unfolding. In laboratories around the world, scientists are probing deeper into quantum mysteries. In space, photons continue their ancient journeys. In your own body, quantum processes sustain life and perhaps consciousness. The universe maintains its quantum secrets while gradually revealing them to those curious enough to look. But the looking itself changes what we see, collapses possibilities into actualities, transforms the quantum into the classical. Questions matter more than answers in this quantum realm. Why does observation cause collapse? What determines which possibility becomes actual? How does the universe maintain superposition across vast scales? What is the relationship between information, consciousness, and quantum mechanics? These questions drive science forward, push us to develop new theories, new experiments, new ways of understanding the cosmos. They remind us that we live in a universe far stranger and more wonderful than everyday experience suggests. It is beautiful that we live in a universe that we can keep wondering about. Each generation discovers new layers of mystery. What seemed like solid answers dissolve into deeper questions. The nature of light, which seemed settled in the 19th century, revealed quantum mysteries in the 20th century that we're still grappling with in the 21st. Perhaps future generations will look back on our current understanding as quaint and incomplete, having discovered new depths to the quantum realm we can't yet imagine. And as you drift into sleep, you remain part of this quiet universe wrapped in its laws, carried by its mysteries gently, peacefully into the night. The photons that brought you the words of this journey have completed their task, collapsing from superposition into definite states to deliver their information. But new photons continue to emerge, to travel, to exist in that strange quantum realm where all possibilities coexist. You're surrounded by this quantum light, immersed in fields of possibility, participating in the constant dance between observation and superposition. Your sleeping brain will soon enter its own mysterious states, processing the day's information, consolidating memories, perhaps exploring its own form of superposition in dreams where multiple realities can coexist. While you sleep, the universe continues its quantum processes. Photons travel through space, particles tunnel through barriers, entangled pairs maintain their mysterious correlations. The cosmic dance of possibility and actuality goes on, whether observed or not, whether understood or not. In the morning, when photons from the sun collapse, their superposition against your closed eyelids, waking you to a new day, remember what you've learned tonight. The light that wakes you has journeyed for 8 minutes from the sun, existing in superposition for most of that journey, exploring all possible paths before choosing one at the moment it reaches you. You live in a quantum universe surrounded by mystery, participating in the strange dance between observation and possibility that shapes reality itself. The universe asks nothing of us except perhaps to wonder, to observe, to participate in the unfolding of reality through our observations and interactions. We are the cosmos becoming aware of itself, quantum systems that have developed the ability to contemplate quantum mechanics, observers made of the same mysterious light we seek to understand. In our wondering, in our observing, in our quest to understand what happens to light when nothing observes it, we participate in the deepest mystery of existence itself. Rest now in this knowledge, in this wonder, in this beautiful uncertainty. You are part of something vast and strange and wonderful, something that maintains its mystery even as it reveals its patterns. The quantum realm surrounds you, sustains you, includes you. You are not separate from the mystery. You are part of it, made of it, sustained by it. And as you sleep, as your conscious observations cease for a while, the quantum dance continues. Photons maintain their superpositions, the universe explores its possibilities, reality unfolds in its strange and beautiful way. Sleep peacefully in this quantum cosmos, this universe of light and mystery, of observation and possibility, of questions that lead to deeper questions and wonders that never cease. You are safe here, held by the same laws that govern the stars, made of the same quantum light that fills the universe, part of the same grand mystery we've explored tonight. Let these thoughts carry you gently into sleep, into dreams, into the quiet darkness where consciousness rests, while the quantum world continues its eternal dance. And in that space between waking and sleeping, between observation and non-observation, between the classical and quantum realms, you exist, peacefully, perfectly, part of the vast and beautiful mystery of existence itself. The photons continue their journeys. The universe maintains its superpositions. Reality waits patiently for observation to make it definite. And you, wonderful quantum being that you are, rest at the heart of this mystery, carried gently into sleep by the same forces that carry light across the cosmos, held by the same laws that maintain the delicate balance between possibility and actuality, between what might be and what is. This is your universe. Strange, beautiful, mysterious, quantum. It whispers its secrets to those who listen carefully, reveals its patterns to those who observe patiently, shares its wonders with those who approach with curiosity and openness. Tonight, you've glimpsed one of its deepest mysteries. What happens to light when nothing observes it? The answer, superposition, possibility, quantum uncertainty, only deepens the wonder. And that wonder, that mystery, that beautiful uncertainty, follows you now into sleep, into dreams, into the peaceful darkness where you rest. Quantum being in a quantum universe, observer and observed, part of the eternal dance of light and consciousness that makes reality itself. End